Deep dive into sklearn, linear model, SGDRegressor. The sklearn, linear model, SGDRegressor is a powerful and versatile tool for fitting linear models. Using stochastic gradient descent (SGD), it offers a range of customization options to tailor the learning process, making it suitable for various regression tasks. Understanding the basics. Linear model at its core. SGDRegressor fits a linear model, meaning it learns a relationship between the input features and the target variable using a linear function. This function can be represented as yw1 x1 w2 x2 wn x nb. Y target variable x1 x2 xn input features w1 w2 wn weights assigned to each feature learned during training. B bias or intercept term also learned during training. Stochastic gradient descent (SGD). Instead of calculating the gradient for the entire dataset at once, SGD takes a sample of the data batch to update the weights. This makes it efficient for large datasets and can help avoid getting stuck in local minima. Regularization. SGDRegressor allows you to incorporate regularization techniques L1, L2, elastic net to prevent overfitting. These techniques add a penalty term to the loss function, discouraging the model from assigning excessive weight to any single feature. Parameter breakdown. Let's dissect the key parameters in detail. 1. Loss function. Loss controls the type of loss function to minimize during training. Squared loss. Standard squared loss function, suitable for general regression problems. Huber robust loss function, less sensitive to outliers compared to squared loss. Epsilon insensitive, used for linear support vector regression (SVR) with an epsilon insensitive zone. Squared epsilon insensitive, similar to epsilon insensitive but uses squared loss outside a epsilon insensitive zone. 2. Regularization. Penalty specifies the regularization technique to apply. No regularization is used. L2 regularization. Ridge regression adds a penalty proportional to the square of the weights. L1 regularization. Lasso regression adds a penalty proportional to the absolute value of a weights. Elastic net combines L1 and L2 regularization, allowing for a mix of sparsity, feature selection and stability. 3. Hyperparameters. Alpha controls the strength of the regularization penalty. Higher values result in stronger regularization. L1 ratio used only for penalty elastic net. This parameter controls the mix between L1 and L2 regularization. A value of 1 corresponds to pure L1 regularization. 0 corresponds to pure L2 regularization. And values between 0 and 1 represent a blend of both. Fit intercept determines if the model should learn an intercept term. Maxiter. The maximum number of epochs passes over the training data to run. Toll. The stopping criterion. Training stops when the improvement in the loss function falls below this tolerance. Shuffle. Whether to shuffle the training data before each epoch. This helps to avoid potential biases introduced by the order of data points. Random state sets the seed for the random number generator used for shuffling the data. Useful for reproducibility. 4. Learning rate. Learning rate controls the step size taken during gradient descent. Constant learning rate throughout training. Optimal uses an optimal learning rate based on the data. Inviascaling learning rate decreases with the number of iterations. Adaptive uses an adaptive learning rate based on the gradient magnitude. Ether 0 initial learning rate for constant and inviascaling schedules. Powered exponent for the inverse scaling learning rate. 5. Early stopping. Early stopping enables early stopping to prevent overfitting by monitoring performance on a validation set. Validation fraction proportion of training data to set aside for validation. No change number of epochs without improvement in validation score before stopping. 6. Others. Warm start allows you to reuse the solution from a previous call to fit as initialization, saving training time. Average computes the average of the weights across all epochs, potentially improving robustness. Verbose controls the amount of output during training. Attributes and methods. Attributes. Core the weights assigned to each input feature. Intercept the bias term intercept. Nitter the actual number of iterations run during training. Methods. Fitx. Y. Sample weight none trains the model on input data X and target variable Y. Predictx makes predictions for new data X. Score X. Y. Sample weight none calculates the coefficient of determination R2, a metric indicating the goodness of fit. Use cases and advantages. SGDRegressor is particularly well suited for large datasets. Its stochastic nature makes it efficient for handling massive datasets. Online learning. It can update the model incrementally as new data becomes available, making it ideal for situations where data arrives in streams. Regularization. It readily integrates L1, L2, and elastic net regularization to prevent overfitting and promote sparsity. Feature scaling. SGD is generally sensitive to feature scaling. Scaling features to a common range can improve performance. Key considerations. Hyperparameter tuning. Finding optimal values for parameters like learning rate, alpha, and penalty is crucial for achieving good performance. Initialization. The initial weights can significantly impact the training process. Experimenting with different initialization strategies might be necessary. Convergence. SGD might not always converge to the global minimum, especially in non-convex loss functions. Balancing robustness and accuracy. Choosing between different loss functions, e.g., squared loss vs. Huber, involves balancing the trade-off between robustness to outliers and accuracy on typical data points. Example application. Python. From sklearn, linear model import SGDRegressor. From sklearn, datasets import load Boston. From sklearn, model selection import train test split. Load Boston housing dataset. Boston load Boston. X Boston. Data. Y Boston. Target. Split into training and testing sets. X train. X test. Y train. Y test train test split X. Y. Test size 0.2. Random state 42. Create and train SGDRegressor. Model SGDRegressor loss Huber. Penalty 2. Alpha 0.01. Random state 42. Model. Fitx train. Y train. Make predictions on test set. YPRED model. Predictx test. Evaluate model performance. Print FR2 score model. Scores test. Y test. This example demonstrates how to use SGDRegressor with the Huber loss function, L2 regularization, and a specific hyperparameter configuration to predict Boston housing prices. By understanding the various parameters, attributes, and methods, you can leverage the power of SGDRegressor to build efficient and effective linear regression models for a wide range of applications.